Hello everyone. In this lecture, we will start a new chapter, which is called the closed formula for the recurrence relations. And we start with a very famous sequence, which is called Fibonacci Sequence. And for all kinds of stories, these sequences associated with these sequences, such as how the rabbits give birth to small ones, you can find on Wikipedia. But here we will only focus on its mathematical significance. So a more general question is like the following. So we consider a sequence A0, A1, A2. We start with A0 because it's easier sometimes to give a formula, closed formula for such kind of sequence. You can start with A1 just by shift the formula by 1. And here we assume AN is given by, instead of a closed formula, we define it by some recurrence relation. The most general form is AN is Fn, An minus 1, An minus 2, all the way to A0. Okay, so here Fn can be arbitrary functions. The only important thing here is that An can be uniquely determined by the previous items. Then a natural question is, can we give a closed formula for An, which means a function depending on n, not on the previous data. And second question is, if you can do that, can we have some, probably it's better to call it A1 star, A1 prime. If you can have a closed formula for An, can you sum them up just as what we usually do? Okay, before we start with the Fibonacci sequence, we first look at some examples. The first example is the familiar arithmetic sequence. We can write in the following form. So An is An minus 1 plus k. K is a constant. Okay, then from the high school mathematics, we know that An is A0 plus Nk, and Sm is n plus 1 A0 plus n plus 1 choose 2 K. You can verify it by yourself, it's not that hard. And then, of course, to sum this up, actually, we mentioned that before. The first method for Sn is given by Gauss when he was 7 years old. And then second example is a so-called geometric sequence. And in this case, the quotient for the adjacent items is a constant, or we can represent the formula in this way. So here, Q is a constant. And the general formula for An is A0 times Qn. And the Sn is A0 times Qn plus 1 minus 1 divided by Q minus 1 when Q is different from 1. And when Q is 1, you just get A0. You don't need to remember the formula. For example, I would say the second one is kind of redundant because if you let Q go to 0 in the first formula and by the L'Hopital's rule, you will have the second formula. Okay, no big difference between them. Okay, so for these two kind of sequences, we have well-known result regarding the question 1 and the question 1 prime. And now the main topic for this lecture is Fibonacci sequence. So far I haven't mentioned what is Fibonacci sequence, but I will just give you right now. So let's call it F0, F1, F2 all the way up, and the relation is given by Fn is Fm minus 1 plus Fm minus 2. So the item is a summation of the adjacent two items before it. And of course, you'll find it's not uniquely determined unless we set up some initial data. Initial data means F0, F1. Okay, so usually we set up F0 equals 0, F1 equals 1. And then you can look at what is Fn. So Fn is the sequence is given by first one is 0 and second one is 1. Third one is summation of previous two, so it's 1. Fourth one, third F3 is summation of F1 and F2, so it's 2. Then you have 3, 5, 8, 13. Okay, now let's look at Sn. So for Sn, so summation of F0 just 0, summation of F0 and F1 is 1, and summation of first three terms is 2, and then you have 4, 7, 12, 20, 33, blah blah. Okay, if you are careful enough, you will notice that actually there's no big difference between Fn and Sn. So the Sn is almost Fibonacci, although not that close. Okay, if you look at that, what do you have? Let me use this color. So 20, for example, is 7 plus 12 plus 1. Okay, and then 12 is 7 plus 4 plus 1, so almost Fibonacci. And if you compare Fn and Sn, then you find some more interesting stuff. That is Sn, so I will just write down. Sn is Fm plus 2 minus 1. So if you follow the arrows I'm drawing, you will see this relation. So there will be conjecture. Okay, And immediately we can prove this. So it's our lemma. For n at least 0, the summation from fm from 1 to n is fm plus 2 minus 1. Okay, let's carry out the proof by induction. So when n is 0, so f0 equals 0 equals f2 minus 1. So this is true, trivially. And now suppose, let's call star. Suppose star holds for all m greater than 0 and less than or equal to k. Consider the case when n is k plus 1. Then what we have fm plus 2 minus 1. So let's call this as right-hand side. This, you plug in the value of n, so it's fk plus 3 minus 1. And then you use the recurrence relation once, fk plus 1 plus fk plus 2 minus 1. And now you can use the assumption, because now k is, for this one you can apply, so apply star to fk plus 1 and fk plus 2. And then immediately we have so probably let's write one more steps. Okay, then you have first fk plus 2 minus 1 equals f0 plus f1 plus f2 plus all the way up to fk plus 1 plus fk. Okay, then next fk minus 1 gives you f0 plus f1 plus fk plus 1 plus fk plus minus 2 minus 1, and you have actual 1. Okay, now when you sum this up, notice that here you have a lot of recurrence relation to use. So you have 1 plus f0 plus f2 plus f3 plus all the way to fk plus 1. And since 1 is f1, so we have the formula for n equals k plus 1 as well. So by induction, the formula holds. Okay, before we give a general formula for Fn, we would like to introduce another property. And actually, you will see in the following that even if you have the closed formula, probably it's still hard to get some actual properties. So I will call this type of sequence, just like Fibonacci sequence, is more complicated than arithmetic one or geometric ones, but it's also more of interest to us because you have some control of it, you have understanding of it, but not all of it. You can always find something new. That's a good research object. Whenever you read something, whenever you look at something, you have new feelings. Just like language is so complicated. Whenever you read something, you can write your own. So that's a good part of language. If you can only write something previous one knows, then it's useless, kind of, because it's closed. So the society is closed. Our development is closed. It's not good. Okay. Now, so the next property is that Fn is even if and only if n is divisible by 3. F0 is 0, F1 is 1, F2 is 1, and then F3 is 2, F4 is 3, F5 is 5, blah blah. And you will see at least for first few terms, this is true. And now, suppose, let's call this as orange star. Suppose orange star is true for n between 0 and 3k, and then consider the case n is less than 3k plus 3. And actually, we only have 3 cases to consider. The first one is f3k plus 1 by the recurrence relation. It's a summation of f3k plus and f3k minus 1. And similarly, you can write down the recurrence relation for the remaining twos. And now, by the assumption, this is even, and this is odd, this is odd, this is odd, this is odd. Therefore, this is odd, this is odd, and f3k plus 3 is even. And by the so we complete the induction argument. We prove the statement. Okay, and the next we come into kind of the main topic of this chapter: how to derive the closed form. So the question is, can we derive a closed? We leave aside the question whether this closed form is useful. Here we only care about how to derive it. Okay, and some observation is as follows. First, noted that the relation is linear. In other words, if you have Fn satisfies this relation, Gn satisfies this relation, then if you define Hn to be summation of Fn and Gn, okay, let me write Hn on this side, then you can conclude Hn is Hn minus 1 plus Hn minus 2. Linear means you can add your solutions. Just like if you learn a little bit Fourier analysis or whatever, you know that the reason why Fourier analysis is useful for linear system because it's also additive. Okay, you can add something together, which is still a solution. Of course, this is not true for nonlinear system. That's why nonlinear system is quite hard for us to understand. We need to develop a lot of advanced tools to deal with it, although still far from understand every nonlinear system. Just like our universe is nonlinear. If it's linear, then everything kind of trivial. Probably we won't have human beings at all. Okay, and if you noted this thing, then how to derive some idea for the closed form. So the idea is we look for enoughly many special solutions to the relation, to the recurrence relation. So here the relation is this one. Later on we will generalize it very easily to some other, a little bit more general case. Okay, so first step, you look for enoughly many special solutions, and then do linear combination of special solutions. Why we need to do this? Because as we mentioned at the very beginning, the Fibonacci sequence, not only the relation, it also depends on the first two terms that we call initial data, so that f0 is 0, f1 is 1. If you don't have any requirement for the initial data, then the special solution is already a solution, so you don't need to work anymore. And just a small remark is, so we know we need to find the enoughly many special solutions, but how many we need to find? So from second part, we know that initial data, this means this too, initial data is all two-dimensional. What does that mean? That means you have two variables, and each of them can be chosen from a real number line. Therefore, if you know linear algebra, the space is two-dimensional. Okay, and then, therefore, we need to find two special solutions to accommodate the initial data. This is because we want to match up with the initial data, therefore you need to have two solutions. This is also a fact due to linear algebra. Whenever you need to solve solve two equations, you need to have two variables. Okay, now what kind of special solutions? And actually, in this lecture and in next lecture, and even in all the study of the ordinary differential equation course, I don't know if you will take that, but if you look at that course, the special form is always the following one. You don't have any other choice, just some variation of it. So if you forget everything, please remember this one. This is a special form. And of course, if this is a solution, then you need to have this one. This is recurrence relation for special solution Fn equals Qn. Okay, then simplify it. You have this one, you factor out Qn minus 2, and then you find the solution. Q1 is 1 plus square root 5 over 2. Q2 is 1 minus square root 5 over 2. Okay, then let's do linear combination. Let's use this color, linear combination. So Fn will be C1 1 plus square root 5 over 2 to nth power plus C0 1 minus square root 5 over 2 to nth power. Okay, now let me use different color. C0, C1 are to be determined. So that's your freedom. You have the freedom to choose variable C0 and C1 to accommodate your initial data. And therefore, F0 equals 0. And now let's look at initial data. F0 is 0, F1 is 1. And if you plug in your special solution, you will find that this is equivalent to C0 plus C1 is 0, C0 times 1 plus square root 5 over 2 plus C1 times 1 minus square root 5 over 2 is 1. And solve it. Let me make a remark. This is a linear a system of linear equations, and you have unique solution if and only if the Jacobi is non-zero. You have the Gauss elimination method. I would emphasize that although Gauss elimination is very elementary and kind of trivial if you already know that, but in fact it's very useful and very fundamental. Okay, if you forget everything in linear algebra, please remember the Gauss elimination. Okay, now you can solve it, and solve it you will find C1 is C1 is 1 over square root 5. C0 is negative 1 over square root 5. And you can write down your closed formula for the Fibonacci sequence Fn. This is true for all n greater than or equal to 0. So this is a closed form. And a little bit variation will be a formula for general or Fibonacci sequence. So suppose the first one is A, second one is B, and the relation is the same. And then by solving the corresponding linear equations, you will find this will be B minus 1 minus square root 5 over 2 times A divided by square root 5 times 1 plus square root 5 over 2 to nth power plus 1 plus square root 5 over 2 times A minus B divided by square root 5 1 minus square root 5 over 2 to nth power n greater than or equal to 0. Okay. So I leave it to you to verify it. It's a good exercise to repeat the previous procedure for solving the Fibonacci sequence. Okay, and you will see that the formula kind of it has advantage that it's a closed formula. You don't need to know the previous data, but also it gives you some drawbacks. Firstly, the computer, when you use this formula to compute something, I guess it gives you no good, because square root 5 give you a lot of decimals, and when you do nth power, you will have some inaccuracy due to the computing. And secondly, from this formula, you cannot even say that fn is an integer, so it hidden something. Okay, so when you have some formula, don't be too happy, and if you don't have formulas, also don't be too sad. Okay, next, we would like to give some combinatorial explanation for the formula or for the relations. So, determine the number Hn of ways to perfectly cover 2 by m board with 1 times 2 dominoes. So here perfect means no overlap. And the solution, so we will like, it's easy to see when n is 1, h1 is 1. You only have one way to cover it. Okay, and when n is 2, now here you have 2 ways. Okay, and we claim that actually Hn satisfies the Fibonacci sequence, the relation of the Fibonacci sequence, that is Hn is Hm minus 1 plus Hm minus 2. Why it is? Because look at proof. Look at the first block on the left up corner. Then you have two choices or two possibilities for the domino covering the first block. So firstly, you might have this one. Secondly, you might have this one. Okay, case 1. So let's see. Case 1, case 2. And then regarding case 1, we must have a horizontal 1 by 2 domino, a horizontal 1 by 2 domino underneath the green one. you must have this one to match it up. Otherwise, you cannot have a perfect covering. Okay, then therefore, then the remaining part, that means after truncating the first 2 by 2 is a perfect covering or perfect cover of 2 times n minus 2. So I will say you truncate and look at this. This is Hn minus 2. Therefore, the number of ways to perfectly cover it in case 1 is Hn minus 2. And then for case 2, you will see after you truncate the first 2 by 1, you will have after truncating 2 by 1, the first 2 by 1 dominants, we have a perfect cover of 2 by n minus 1. Therefore, you have Hn minus 1 ways regarding case 2. And therefore, totally, Hm should be Hn minus 1 plus Hn minus 2. Okay, and then we can consider the following slightly degenerate case. This actually is easier than the previous one. Determine the number Hn of ways to perfectly cover a 1 by m board with 1 by 1 or 1 by 2 boards. Solution. Similarly, H1 is 1, you only have one choice, and H2 for H2 you have 2 choices. Firstly, you can use 2 1 by 1 blocks to cover it, and or you can use a 1 by 2 board to cover it. And also you have Hn equals Hn minus 1 plus Hn minus 2. You can prove it in a similar way, but another point of view is another solution. So let me call this first one example 1, second one example 2. Example 2 is just the first row of the configuration in example 1. Okay, if you look at the first line, so let me use a different color. Oh, sorry. For problems in example 1, you have this, and you have different way of perfect cover. And now if you look at first row, that corresponds to the question in example 2. For example, you have this, and you have this. Okay. And another, you don't think, so I want to make a remark that you don't think the problem of perfect cover is very easy. If you change it to the following question, how many ways to perfectly cover 3 by m by 1 by 2 dominoes? That would be very difficult. Okay, I leave it to you. You can search online to see if there's some work on it, if you have interest. Okay, another interesting property is the Fibonacci sequence has a relation to the binomial coefficients. So we first look at the collection of all the binomial coefficients organized as a Pascal triangle. Okay, now you draw lines, the screw lines which intersect the horizontal line with a 30 degree. Then what do you have? Then you have this kind of lines. And if you do summation, you will see the first summation is 1, and summation is second line. So L1, L2, L3, blah, blah. Summation 1 is 1, summation L2 is 1, summation L3 is 2, summation L4 is 3, summation L5 is 5, summation L6 sorry. Okay, never mind. Is 8 and blah blah, and then you will notice that you have a Fibonacci sequence. Appearing in the Pascal triangle when you do some summation. And then if you write down the observation mathematically, there will be summation of m minus 1 choose 0 plus m minus 2 choose 1 plus blah blah all the way to m minus m plus 1 over 2. The floor m plus 1 over 2 floor minus 1, this will be Fm. Fn is a Fibonacci sequence. And the proof, from the previous study, we have the feeling that when you have recurrence relation, it's quite suitable for induction argument. Okay, so we will also use that method in our proof. Okay, for convenience, let's denote the left-hand side by Gn. We want to prove that Gn equals Fn. Okay, so when n is 1, so we have G1 is 0 to 0, which is 1, so it's F1. When n is 2, G2 is 1 choose 0, which is 1, which is F2. When n is 3, G3 is 2 choose 0 plus 1 choose 1. So this is 2, which is F3. Okay, now suppose star, so let's call this as star. Suppose star holds for n less than or equal to m. Consider the case n equals m plus 1. And you can write down the definition for m plus 1. Okay, now you use a Pascal identity for each one. So for first one, you have, this is m minus 1, 0, plus m minus 1 choose negative 1, so it's 0. And then you have m minus 2 choose 1, m minus 2 choose 0, blah, blah, all the way down to m minus m over 2 floor minus 1 m over 2 floor plus m minus m over 2 minus 1 m over 2 floor minus 1. Okay, and then we need to split the question into two cases depending on the parity of m. When m is even or m is 2k, then first few terms are not that important. You can still keep it. M minus m over 2 minus 1 m over 2. Okay, let's write last two terms. Over 2 minus 1 m over 2. Okay, and then you plug in, you will find this is actually k choose k minus 1. This is k minus 1 choose k. So this is gone, this is 0. And below 1 is easier. All the way to m minus m over 2 minus 1 m over 2 minus 1. And then it's easy to see the first line actually is gm. The second line is gm minus 1. This is a more subtle case. When m is odd, everything makes sense. So this is first line, and then you have the second line. So which is gm plus gm minus 1. This is the first line is gm, and the second line is gm minus 1. Okay, therefore we are done. Okay, and or if you still cannot see it, I can write one more steps. Then you have, by assumption, this is Fm plus Fm minus 1, which is Fm plus 1 by the property of the Fibonacci sequence. Okay, now I would like to show you a second proof, which is a more combinatorial flavor. So we still, by the example 1 we showed before, we transform the Fibonacci sequence into the perfect covering problem. Okay. So we consider the perfect covering. Okay, and now, so my feeling is that whenever you have new point of view, more or less equivalent to say you have a new kind of way to compute something. You divide the problem into subclasses in a different way. So here, what we do is we care about the horizontal blocks. So we care about these horizontal blocks. Okay, and and you can see that Gn actually is a summation of k from 0 to n over 2 floor, the number of configurations of perfect covering with k horizontal blocks. Okay, and denote the first column, the number. So let's give index for each one. Different color. Okay, 1, 2, 3, 4 to n for different color, and denote the index of the first column, indices of the first columns of the horizontal blocks by A1, AK, A1 to AK. In other words, if you need a slight explanation, that means first block occupies A1 and A1 plus 1's columns, and etc. Okay, and then you can write down in this way, and also we have the property the adjacent AK has difference at least 2, otherwise you have overlap. Okay, now we do the transformation, a change of variables, and then this is kind of the way we deal with the problem when we do some we find a number of integer solutions for some according to some linear system of inequalities. So then you still have the increasing property, strictly increasing, but you don't have the let's see, gone. This is gone. You don't have this assumption anymore by our change of variables. Okay, now, so the configuration with k horizontal blocks is one-to-one correspond to the sequence B1 to BK. So let me write. With K horizontal blocks is one-to-one correspond to sequence B1 BK such that they increase sequence from 1 to n minus k. And then, of course, if you take you compute the cardinality of the set, you will know that the number is m minus k, choose k. Okay, therefore, you have Gn is summation, Fm plus 1 equals Gn. That's by our previous study. And then equals k from 0 to n over 2, n minus k, choose k. And you shift it by 1, you can derive that Fn is summation for k from 0 to n minus 1 over 2, n minus 1 minus k, k. Okay, next we generalize the above method to more general, but not the most general case, more general linear recurrence relation. So we do the following setup. So suppose you have a sequence H0, H1, H2, Hn, blah, blah, is set to satisfy a linear recurrence relation of order k if exists functions a1n, a2n, akn different from, the last one is different from 0, and also bnn, such that Hn is a1 times Hn minus 1 plus a2 times Hn minus 2 plus ak Hn minus k plus bn. So n is greater than or equal to k. Okay, and here recall that order 2 means that on the right hand side you have k. The formula relies on k pieces of data from previous items. Okay, and of course, for this general question, we have no way to deal it with a closed form. We only deal with some easy case. But before it, we first look at some other examples. First one is Dn, the derangement numbers, and recall that we do have formulas for this one. This is order 2. But we have another one. Recall that we have a lot of relations for derangement number. This is order 1. And if you still remember the formula for Dn, you notice that you recall that you have n factorial, and then inside you have 1 minus 1 over 1 factorial plus 1 over 3 factorial plus blah blah whatever. And you have a lot of fractions, it's no way like the closed formula to the Fibonacci sequence. The reason is that look at the coefficient here. The coefficient is changing. It's dependent on the variable. That's why it's complicated. Okay, and for complicated doesn't mean you cannot solve it. Just means in general, if you have two complicated coefficients, you may have trouble to derive a general formula. And another one is this, and actually this is n factorial kind of. And also, you will have some other one, just like the geometric sequence. Geometric sequence. Okay, and so the remark is, in general, it is hard to solve. Just like what we did in ODE. When you have coefficients as variables, then it's very hard. Okay, and I will not explain the notation homogeneous, but if you learn some ODE or linear algebra, you know, it means Bn is 0. And then we have constant coefficients. Are constant. So in the following, we will solve the problem underneath these two assumptions. It's still quite general, including the Fibonacci sequence and the geometric sequence and any other very complicated sequence. Okay. And the idea is similar, but notice that now, how many initial data we need to accommodate relations of order 2, order k need to prescribe H0, H1, Hk minus 1 k relations. Sorry, k data. So idea is still same. Find enough special solutions. So actually, of order k, you need to have k special solutions and do linear combination. And as I said before, you don't have any other choice. Let's assume the special solution takes form Qn, and then you plug in the relation you will have Q0 is Qn minus A1, Qn minus 1 minus A2, Qn minus 2 minus AK, Qn minus K. And you factor out Qn minus K, you will find inside you have a polynomial of degree K, depending on invariable Q. That's why we call the relation order Q, because inside the associated polynomial is a polynomial of degree K. And then Q is a solution of the polynomial equation. Okay, now we can state the theorem. If xk minus a1 xk minus 1 minus all the way down to minus ak minus 1x minus ak has k distinct roots q1 to qk, then Hn equals C1 Q1 n minus 1 plus C2 Q2 n minus 2 plus all the way to CK AK QK to here you have Q minus 1 plus qk n minus 1 is our general solution. So just a small remark, what does a general solution mean? It means for any initial data H-lin, H1, HK minus 1, there are constants C1 all the way to CK, so that the corresponding star is the unique solution to the corresponding problem where the recurrence relation is given by A1 HM minus 1 plus A2 HM minus 2, blah, blah. And H0, H1, all the way to HK minus 1 are prescribed. So the proof is quite easy if we admit some linear algebra effect. So assume star, then we have H0, H1, HK minus 1 are prescribed. Means that if that is a solution, it means that H0 is C1 plus C2 plus all the way to CK. H1 is C1 Q1 plus C2 Q2 plus all the way to CK QK. HK minus 1 is C1 Q1 K minus. Oh, here I made a mistake. Here you don't have minus 1. The power is n. And that doesn't really matter because you can redefine C1, define it to be C1 times Q1, then you have a new formula in the previous form. Not a big deal. Okay, and you noted that by linear algebra, this delta has a unique solution for any H0, H1, HK minus 1 if and only if the determinant, you just take out the coefficients and the determinant is different from 0. Okay, this is bilinear algebra. And if it's not 0, then the solution, if you have solution for delta, is depending on the actual procedure for the from the Gauss elimination. You have different choices. It's more complicated. But then say you don't have solutions. It depends. Okay, so if this is true, why this is true? This is so-called Vandermonde determinant. And you can actually compute it. It will be product of Qj minus Qi for all ij between 1 and k, such that I is less than j. And since we assume the polynomial equation has distinct rules, so this is non-vanishing. Okay, now we apply the previous theorem to some actual examples. Suppose you have a recurrence relation of order 3 and with 3 initial data. And we first look at characteristic polynomial and factor it. You have 3 solutions. And then the general solution is given by, notice that these 3 solutions are distinct. And then you have general solution C1 times 2 to nth power plus C2 times 1 to nth power plus C3 times negative 1 to nth power. And all you need to do is accommodate the initial data. And then you plug in the formula for n equals 0, 1, 2. And then you can solve. C1 is negative 1/3, C2 is 2, C3 is negative 2/3, and Hn is 2 minus 2 to nth power over 3 minus 2 times negative 1 to nth power over 3. Okay, next let's look at some real problem and find the number Hn of sequences of length n of the letters A, B, C, such that the adjacent letters are different, and the first and the last letters are different. Whenever you have a new problem, it's a good habit to start with some simplest cases. So for example here, for H1, it's easy to see you don't have any such sequence because the first one is the last one. And for H2, it's a cardinality of the set AB, AC, BC, BA, CA, CB. So it's 6. And for higher cases, so we look at that Hn can take the following form. So case 1, A1 is AM minus O. So let's still give some index for each position. H1 is AM minus 1. Then what do you have? You have the following possibilities. Here you have, you have A and A here, and of course you can have B. C. And then you noted that for the last position, you can fill in B, C, A, C, A, B, 2 letters. And before it, if you consider the first n minus 2 letters, so there will be a problem or such a sequence according to n minus 2. Okay, so for each one, you will see that the number of sequences in case 1 is 2. 2 is according to 2 choices for the last position times HM minus 2. HM minus 2 because you do the truncation. Only look at first m minus 2 positions. Okay, now for case 2, of course, a nature definition is A1 is different from AM minus 1. Then you have a lot more choices. I will just enumerate some. Okay, if the first one is A, and since AM minus 1 is different from A1, so this one will be B or C. And the last one, because it's different from B, different from A, then you can only put it in C and then put it in B. Okay, and similarly here, if you have B and AM minus 1 can only be A or C. No matter what you choose, the last position is fixed. Okay, and of course you have 2 more. Yeah, for complicated, I will also write down it, but I guess you already know it. Okay, and then we do the truncation, not from 1 to n minus 2, just from 1 to n minus 1. Then you will see it's exactly the question according to n minus 1. Therefore, we can conclude the number of sequences in case 1, in case 2 is 1 times HM minus 1. Therefore, HN HN is 2, sorry, is hm minus 1 plus 2 times hm minus 2. And then you can solve it like hn is 2 times negative 1 to nth power plus 2 to nth power. So I leave this to you. To carry out the actual procedure. Okay, we end up with the following one. So let hn be the number of words or lengths n in three numbers ABC such that no two adjacent A's and firstly you can just compute by hand. H1 is 7, H1 is 3, H2 is 7, and for this reduction or recurrence relation, we need to truncate, and we consider the first position. And you have 3 choices: first, B, or C. Our first one is A, then the next one will be B or C. Okay, and for the first one, you can just truncate starting from the second position. Okay, and then for the here is case 1, here is case 2. Case 2, you truncate from the third position. Therefore, here you have totally the number is hm minus 1 times 2 times 2. Okay, 2 times hm minus 1. And on the right hand side, you have 2 times hm minus 2. Okay, therefore the recurrence relation will be this one. Hn is 2 times hm minus 1 plus 2 times hm minus 2. And to carry out the previous procedure, we can conclude the following complicated formula. Anyhow, it is at least a formula, a closed formula. Okay, I will stop here. Next time we will discuss the case when you have repeated roots. That will be more complicated.